This is an episode on the human visual system and display systems, and it covers the optical part of the pathway of a visualization communication from a machine to a human being. So we're going to look at the human visual system, display systems, and about how the two interact, what you can hope to present on a display system optically. So we're going to look firstly at things that the human visual system can't do. What can't we see? What's not possible to perceive? So you'll see a test in a second, and you're going to see a movie of two teams of students playing with two basketballs. One team wearing white shirts, one team wearing black shirts. That gives you a high contrast between the players. And your task is to count how many times the white team passes the ball during the movie. This is a film from Daniel Simmons, and it's The Monkey Business Illusion. Okay, well, I hope you enjoyed watching that. Now, the question is, how many times did the white team pass the ball? So go back through the movie, look out for things that are not basketballs and are not people, and see what you see this time. And roughly a half of you will see something quite different to the thing that you saw on the last time you looked at this. So the eye doesn't see everything. The brain doesn't perceive everything. You don't think about everything you could think about at a moment in time, even in the area you're in and you're looking at, let alone all the other parts of the world around you. So we're going to look at the limits of the visual system. You'll probably be very familiar with this, but this is just a beginnings of a discussion about light. So light's visible electromagnetic radiation. It's part of a whole spectrum of electromagnetic radiation, going from infrared on one side to radio waves on the other side. There's a whole range of wavelengths. And the visible spectrum is quite a small part of that, but the eyes are designed to detect this in a range from about 380 to 760 nanometers. So that's very, very small wavelengths. The eye is the first point at which light enters the perceptual system. It comes through the pupil, it comes through the lens. The pupil's job is to control the quantity of light coming through so that you see a reduced or increased brightness in a scene equally well on the back of the retina. The lens's job is to focus, and focusing actually only works for young people, and once you get over the age of about 40, your lens stops being flexible enough to do the focusing, and then you will often either need short-range or long-range correction for reading or for driving, depending on which way it goes. But in a younger person, your lens is flexible and will control light such that a focused image appears on the retina, so a clear, sharp image on the retina. We talked about the retina. It's a very sophisticated organ. It does a lot of functions on light that help you see things. But for now, we'll just treat it like a camera film. It detects an image and it sends it through the optic nerve back through into the perceptual and cognitive systems in the brain and the mind. Okay, so here's a question. Which of the orange coloured circles looks the biggest to you? You're probably going to say right. Well, perhaps it's not obvious, but they're both the same size physically on the screen. And the difference comes about because you make relative judgments of size relative to the environment in which something appears. So, first, perceptual cue size. We can't rely entirely on our perception of size. This is an image which, how you perceive it does depend on the size of display, but if you're viewing this on a desktop PC or a laptop, or even a mobile phone, you'll probably see motion in it. It's not a video, it's a still image. If you try and stabilize your eye, so stare at a single grain of rice on here, the illusion stops. And it's a function of peripheral and central vision. But imagine you're a microscoper looking down a microscope counting cells, and they suddenly start moving. How do you know that movement is the cells? Perhaps they're alive and moving, or just a feature of your perceptual system. Okay, so we've looked at size, we've looked at motion. This is brightness. You're getting the hang of it probably by now. Which square is brighter, A or B? Answer, they're the same brightness. It's the relative environment around them which gives you a perception of difference between brightness on square A and square B. If we join them together, it helps you see that. because the whole area now has the same brightness. And if you measure this with a luminance meter rather than judge it by eye, you can tell that exactly the same value of grayscale on the screen. Here's another similar illusion. If you're using gradients in images and in backgrounds, which is quite common, a sunset type gradient across the back of an image, anything you put in front of it will appear differently bright. Now you can use this in a design to highlight something, or you can realize that if you're trying to convey information with a brightness level, the relative brightness judgment that you make may not be accurate. So watch out for gradients in backgrounds. Size, brightness, motion, color. How good's color perception? You probably feel it's quite good for most people. Some people have a deficiency, red green deficiency. Some people are colorblind. Very few people, in fact, are colorblind. In this test, we're going to look at these grey squares, and it's important to try and keep an eye on them. I'll try and point them out in a second. They're going to be in the same place as you see them now in the next slide, and they're going to be the same grey colour. I emphasize that. Okay, so now we move to the next slide. So you'll probably see here some blue squares, and you'll probably see here some yellow squares. That is, you'll perceive them to be blue and yellow, and you may not believe it. They are exactly the same as they were on the previous slide. I'll go back. This grey colour hasn't changed. And if we zoom in enough, you'll be able to see that. So the question is, what's going on here? And what's going on is, if you look at the surround, one of them looks quite yellow, one of them looks quite blue. The illuminant, the light source illuminating this scene, has been designed to be different in each case, in the sense that one of them is a blue light, one of them is a yellow light. Now, your brain looks at this and says, okay, I'm seeing a square, the colour I'm seeing for that square is grey, but the scene is entirely yellow, illuminated by yellow light. Therefore, if I'm seeing a grey square when it's illuminated by a yellow light, actually in real life it must be a blue square. So I'll tell you it's a blue square, and it is almost impossible, if not actually impossible, to change your mind's view of that fact. And similarly on the other side, the scene is illuminated with a blue light, and your brain's saying, oh, it's a grey square, it's illuminated by a blue light, it must be yellow. So it corrects for you to a colour that it thinks it must be. We know that it hasn't changed from this colour. This is Retinex theory, illuminant theory. Land, who invented Polaroid, discussed it, and others too. Okay, 3D. Well, I think the 3D illusions are quite well known. This is the Ponzo illusion. The two rectangles on the left are the same size in screen space, but because they're put into a 3D view, your brain interprets them in perspective. And this is an important thing to remember. The brain works in 3D. It doesn't work in 2D. Flat screens are not natural perception. I mean, it can do it, but it's not a natural environment for perceiving things in. And very often you'll perceive things as within a 3D context. And this illusion works even if you draw two very abstract tram lines. I'll show you a couple of films, or there'll be a couple of links to a couple of films now. One, the Charlie Chaplin film, one that Ames window, and both of these illustrate in real-world scenes how, in the Ames window case, you use perspective to judge the shape of something. The Charlie Chaplin one is interesting because faces you are uniquely designed to recognize and see faces, and the flipping that happens in that illusion, it's very hard to stop, almost impossible, if not impossible to stop. And it shows you how often the brain overrides what you see to replace it with what it thinks you should see, or what it thinks the world really is. So perception from this is not only is the brain a limited perceptual device, it makes up its own idea on what's happening in the world. It makes hypotheses, and it will accept its own hypotheses over the physically sensed perception of what's there. If you remember the grey squares in the coloured cube, it will take its own perception of yellow or blue over the actual physical colour of grey. So why study it? If we're doing visualization, we want to produce visuals and digital images we want to communicate information to people. So if we put things into images you can't see, it's a waste of time. So we want to know what you can and can't see. We want to avoid creating odd distractions in images that influence perception. And we also need to be very aware of creating a false impression of information. We've seen something of human perception. If you want to understand more, there's a whole branch of psychology on vision and visual cognition, how we perceive and understand images and understand how we use images in decision making and in actions that we take. We'll now move on to look at the canvas, the electronic displays that we draw our pictures for. Here's some examples. Desktop monitors and TVs these days are extremely good at very high range of colors, very high resolution, and quite a good range of brightness. Not really real world brightness, but still you can get pretty bright pictures on modern monitors. Tablets and mobile phones are a whole new class of displays in the last 10 or 15 years. Very high resolution, very close to the eye, slightly different features to TVs, but from a visualization viewpoint, not so different. A lot of the difference is perhaps to do with the interaction that you might be able to use on a tablet or a phone. The lower left there is one of the Formula One simulators that are used for training Formula One drivers. I used to work with the Mercedes Formula One team briefly, and we looked at all sorts of things there. One of the most important characteristics there was refresh speed, the number of times a second a picture is changed on the displays. And that's because when you're simulating or driving around a corner of a Formula One car, the background, the distance background, can move so quickly that it breaks up in a very difficult way. VR headsets are interesting. They try and produce a wraparound experience, not unlike the Formula One projection displays, but by wearing them on your head. There's a lot of reasons why that's not a good ergonomic idea, but it's a very popular idea in the literature and a very popular idea in culture that you could have your own view of everything. It's really quite difficult to achieve a good view for these systems, though, in a cheap system. There's some very expensive systems which work very well. So, the very basics of a display, there's this thing, a pixel, which is a small element on the display. It's a contraction of the word picture element. It was a term IBM came up with a long time ago. And the best way to look at this is it's the smallest addressable area of color on a display. 1 pixel is the smallest color point you can put on a display. So what do we mean by color? We've seen color perception doesn't always work, but in most electronic systems, color is produced by a mixture of 3 primary colors, red, green, and blue, and they're added together to create the sensation of any other color that you need. So red and green, for example, will give you yellow, and this additive color system is usually the one that works in displays. Okay, then there's a question about, so we've got a display, we have these picture elements on the display. How many picture elements? What's the most number of picture elements that you want to put on a display? This is a quick calculation based on a standard measure of visual acuity. So you have a person viewing a display. The visual angle A is the smallest thing that you could see on the display. So what's the smallest size of a pixel that you could actually identify as separate from other pixels? If A, the visual acuity, is 1/60th of 1 degree, so 1 arc minute of angle, which is quite small, then the smallest pixel size that you should be able to see on a display is 0.09 millimeters. So a standard 2 million pixel desktop display will have a pixel size of about 0.3 millimeters. So your standard PC monitor or Mac monitor will have this. So that's about 3 times higher than the acuity of 1 arc minute would suggest we need. So you could have at least 3x3, which is 9 times the number of pixels on a screen than a HD 1920 by 1080 display would give you. So you could easily get 5760 by 3240 pixels on a display, 18 megapixels. We can ask a question about Apple's claims on their Retina displays. These change all the time, but on this one, which was the iPad 3, it had 2048 by 1536 pixels, and it had a pixel size of 0.096 millimeters. This is almost at that 1/60th of a degree 1 arc minute resolution. So is that good? Well, 1 arc minute is what's called 20/20 vision. But in fact, 20/20 vision is kind of a norm of good vision. It's not by any means the best a normal person can achieve. And it's not the best that someone with really good visual acuity could achieve. Many people have much better than 0.6 arc minute visual acuity. And if you can imagine vernier acuity and hyperacuity, it goes up to about 0.13, so almost 9 times better. And that's one of the reasons that you can see power lines and telegraph wires in the distance. They're tiny, tiny things. You shouldn't be able to see them, but your visual system can pick them up. So if you go to the very limits, instead of the 3 megapixels on the display that Apple's selling you as a Retina resolution display, you'd need about 50 megapixels. You can look at a table that calculates different resolutions for different displays. And if I look at the Samsung Galaxy Tab, the Dell desktop monitor, and the Samsung TV, there's only one of them in one viewing condition that actually gets to the limit of human visual perception. And that's the Samsung TV when you're sitting about 1.72 meters from the display. And that's because the further back from the display you get, the smaller the visual angle of the pixels. So they eventually reach the limit of visual perception. And if we're talking about 1 arc minute, which is 20/20 vision, which as we said is just normal rather than the best, the Samsung TV is the only one that reaches that. Another feature of brightness is display brightness. Brightness is a very subjective thing, and it depends on the brightness of the environment. If you sit in a dark room and switch your mobile phone on, it will look extremely bright, painfully bright even. Whereas if you switch it on outside in the sunlight, it will look too dim, and you might not even be able to read it in some cases with some phones. So brightness is subjective. It's the degree to which an area appears to exhibit more or less light. And if you want to objectively measure this, you need to define a measurement called luminance, and it measures the amount of light power. Remember we talked about light waves? Well, the power of those waves, the height of those waves, the amount of light power coming from a point is what luminance measures. If you turn that into display terms, it's visible light, it's candelas per meter squared or nits. Contrast is different. It's a ratio, it's a brightness to darkness thing. And you ideally want displays with a really low dark black level, 0 ideally. And it used to be that certain TV companies would promote their products as being the blackest or the best black or high black, because they knew that very low values of black, a display that could show a low black value, was going to look more zingy, more contrasty. And that's important because high contrast makes things readable. Text looks a lot sharper and more readable if it's high contrast. So it's not an absolute level of brightness that's important, it's the contrast levels that are important in displays. And here's an example of how that works. If you look from left to right, these are low and high brightness. And if you look at the top row, the contrast is low. So whether it's low or high brightness, if the amount of light power coming from a surface is low or high, it's not that your perceptual system is responsive to most, it's contrast. And the bottom shows you that contrast. The peak difference between background and foreground will give you a key standout feature. And contrast is important in all of the visual cues that we use in visualizations. What can we see? So we've looked at what we can't see, where the visual system doesn't work. We've looked at what displays can and can't do that we can see, but what things in images should we try and aim for? This is a much harder question and isn't studied scientifically anywhere near well enough. There are a few people in the world who do this. Ruth Rosenholz at MIT is one person who's very interested in what things work in visualizations, and that's what we're after as visualization builders and creators, the things in pictures that work and convey information well. What do you notice? Here's a picture of a rose. You can prime the visual system to see things. There is something very visible in this, and if you've seen it, well done. If you haven't, I'll tell you it's an animal, and it's hidden in the picture of the rose. And some of you might find it knowing that. Maybe the majority of you will not find it. And this works better in a classroom than it does one-to-one, because if you see it, you see it. If you don't, you don't, and you'll think, what is he on about? But for those people who don't see it, if I prime you and I say, okay, well, look, there's a picture of a dolphin in there, and this is the shape it is, you can almost instantly find it. And it shows you that priming is very important in visualizations, and that's why it can be very important to have a key for the important things. So you'll know maps have keys on them. Visualization should come with some keys for the important features at the very least, but ideally for everything. This process of showing you something and then asking you to search for it is known as priming, and in visual search, if you talk to psychologists, it's critical. But it's important to know that you're most efficient at only searching for a single type of feature or a single thing at once. If you ask people to search for things that have two features that are a conjunction of visual features, so you say, for example, look for all of the blue colored triangles in the image, that will slow you down more than if you said look for all the triangles or look for all the blue things. We touched on what you remember when we talked about Michelle Borkin and her work on naturalistic elements in images to make them memorable. It's a good question what you remember, and the information flow from light to thought is stored in a number of types of memory in the brain. And a simple model of this is that you have iconic memory, which stores things for about a second, short-term memory, which will store one or two things, be up to 5 things, and then long-term memory, which stores something of everything that we encounter. You can recall lots of things, but it doesn't store everything. It's quite easy to overload the visual system, and the visual system, if you provide too many things at once, will just stop working or will work very slowly. And here, there's probably too many line graphs here, and if you wanted to pull out a message, you would be better off splitting them into separate graphs, or individual one for each line, or separate graphs for each type of coherent trend, so you have patterns that are similar in different pictures. So then there's a question of what stands out in pictures. Not everything that you see stands out, and if I ask you in the top picture to search for all of the 5s, you would spend a while individually going through every line to do that. Whereas in the bottom image, they stand out because there's contrast. So there's 1, 2, 3, 4, 5, 6, straight away tells you how many there are. This notion of pop-outs are very important characteristics of the visual system, and it's a contrast thing. What feature contrast you use to make it happen is a design decision. I mentioned Ruth Rosenholz's work at MIT. This is some work by Colin Ware, who was originally a British psychologist, trained at Durham, was moved to New Hampshire in the US. And he's looked at all the possible visual cues that will stand out from a background. And you can see, I'll just pick out a few, the grey value, whether or not you've got a sharp vertex, whether or not something is concave or convex, whether it's got a shadow or not, but also some more complex ones like is a shape blinking, is it moving a different direction, or is it moving a different phase to other things. So pop-out is usually best when there's a single feature you want to highlight. Do all differences work? Well, here there is an inverted T. It's actually not as easy to find as the big bold T. So not all contrasts work equally well, and you need to check you've got enough Q contrast for something to stand out if you want it to pop out from the rest of a visualization. Okay, question. Can you do pop out better? Can you learn? Well, it seems unlikely at the moment that we don't think you can improve your pop-out abilities. We have to design them into images and make sure we keep them there. If you want an urgent, important thing to stand out, make sure you use a visual cue channel that will pop out automatically. Don't rely on people learning it over time. So this simple example here, try and find all the 6s, is just as hard as the 5s on the previous page, but find the dot, you'll see it straight away. So if you highlighted the thing you're interested in with a dot, in this case, you'd always find it quickly. Here's a bit about Q combination and an image about that. There are, in here, green circles and green squares. You will find it hard to find all the green squares. There's 3 of them, 2 in the bottom right and 1 in the top left. So this Q combination doesn't always work well. You can see the red things and you can see the green things. You might be able to see the squares versus the circles, but to find the conjunction, the square that is green, as opposed to all the squares that are red, that's a bit harder. So that's something known as the dual target cost. So in fact, if you add any number of visual cues above 1, it's usually going to make it harder for you. But where can you combine cues? Well, these are some that Colin Ware tried out, and these are all designed to be independently searchable in the same image. So you could easily find them if you showed them in the same diagram. Okay, so to wrap up, what are the key points to understand about the human visual system? It's limited. I think that's the key point to understand. Short-term memories have got a limited capacity, so don't show people a lot of information all at once. Show them small chunks. 3, 4, maybe, not many more than that. Visual search is a mechanism you primarily use to see, so you hunt for things in pictures, but actually you also see in the periphery, and you can see what you are seeing around the point you're attending to in parallel with the point you're attending to. And in particular case, if motion happens in your peripheral vision, that's a great pop-out effect. Okay, well, thank you for that. It's a fascinating area which we've only touched on tiny parts of, and if your visualizations are going to work in the future, keep your eye on the psychophysics and the measured literature, the scientific literature about what you can and can't see. It will help guide you through the process of making visualizations that work well.